I see that there's one more question from Azaf, but we don't have the time. If we can move that to, I'm sorry, we can move that to Slack. You're also moderating the discussion afterwards, so feel free to move it there. Thank you so much, Gimba. Thank you so much for super interesting talk. And our next speaker is in person. Greg Marcel is going to talk about why Lense-Thirring solid body precession cannot produce the low frequency QPOs. Greg, you can take over.
Can you hear me on Zoom?
Yes.
Oh, because that's a bit weird. I'm muted, but yeah, it's all right. Oh, good. So thank you, Matthew and Gibwa, for those talks about QPOs and the Lense-Thirring, because it allows me to go straight to the point and not really introduce QPOs. So that's great. So hi, thank you for organizing this, because as you can see, I work in the UK now, so having some sunshine in Italy is just wonderful. And today I'm going to talk about Lense-Thirring precession and whether it fits or not with the theory and observations that we have on accretion flows. So with Matthew and Gibwa, we've seen a lot of information about numerical simulations. I'm going to go on the theory and observation side. So I'm first going to introduce you Lense-Thirring precession a bit, just for a few minutes. Talk about the conditions in which it works and in which it doesn't, and then see whether we can tell if it does or not. So we're also going to talk about accretion speed and alpha in the disk. So first, let's talk about Lense-Thirring precession. So in the model, it assumes an accretion flow and a black hole, as most models do. And accretion is mainly driven by the viscous torque, as you can see here. I'm not going to discuss too much about this equation, but I just want to introduce it. And then they assume that there's another torque in the disk, the Lense-Thirring torque that you can see at the top right here, that contrary to accretion, makes matter move vertically in the disk. And that's the interplay between those two torques that is going to be interesting. As you can see, it also assumes that there is an angle between the black hole spin and the accretion flow. Theta, I'm also not going to really talk about that because it's not supposed to really matter in the Lense-Thirring precession model. But the question is, what happens when one of them is bigger? What happens when the viscous torque is bigger? What happens when the Lense-Thirring torque is bigger? What are the conditions? So if you compare those torques, it's been done about 10 years ago by Nixon. If you compare those torques, you have this expression. I'm just going to talk about the expression and the terms. So on the top, you have the spin of the black hole, the inclination of the disk. Those depend on the source. I'm just going to assume that this is one for this entire talk. So we are in the worst conditions possible. Lense-Thirring is just the strongest it could be. Then at the bottom, you have the actual structure of the accretion flow. So you have alpha, which was introduced by Matthew, so thank you. And you have the aspect ratio of the disk, also introduced by Matthew, so thanks again. So it depends on those two parameters a lot, as you can see, alpha and epsilon. H over R, I'm calling it epsilon for the entire talk. And then you can see that there is a radial term. So you can see that the ratio decreases with radius. So if you revert that, it means that the closest you become to the black hole, the more dominated or the more likely you will be dominated by the Lense-Thirring torque. So your picture should look like this. Like the closest you become to the black hole, the more you're going to be dominated by Lense-Thirring. So you have a break radius at some point in your flow. This is exactly the picture that was imagined by Ingram et al. In 2009, where you have your viscous torque and then your Lense-Thirring torque in the inner regions. Now the question is, what happens when your Lense-Thirring torque dominates? Well, you have two different possibilities according to their studies. The first one is the diffusive regime. So you have alpha, your viscous torque, your viscosity, sorry, that is much bigger or simply bigger than epsilon. So alpha is bigger than the aspect ratio of the disk. If that happens, in the green region, which is where the Lense-Thirring torque dominates, you're just going to align with the black hole spin. This is the Barden-Peterson configuration. You have a great paper by Matthew, by the way, from 2019, where he shows that configuration. He showed it again today. So the disk is going to align with the black hole spin, and you're not really going to see QPOs because then your disk is not precessing, it's not oscillating. So you're not going to really see QPOs, or at least not the geometrical ones. And the second regime is the one that interests us, is the wave-like regime. So the idea is that in this case, alpha, so the viscosity is much smaller than epsilon. So now your disk is going to act like a solid body, and every annuli in the disk is going to oscillate. They're all going to oscillate together, and you're going to have a beautiful picture, which is this one, where you have your disk oscillating like a solid body, sorry, on a frequency that depends on some parameters of the geometry. So this is the wave-like regime, and this is the one imagined about 10 years ago to be able to explain QPOs, where your geometry, like it's a geometrical effect, basically. And this is the one we're interested in. This is the one we're trying to get. Now, the question is whether we actually get it or not, because this has shown unprecedented and impressive results in explaining QPOs. But the question is, are we really in that configuration? Because we have two conditions, again, bigger Lense-Thirring torque and bigger alpha than epsilon. So let's now dig a bit into the equations. I'm not going to write many more equations than that. I'm just using the basic accretion flow equations as you can see them, just making the assumption that the disk is not too thick. So epsilon is not bigger than 1. If you take those equations and you combine them, you can derive the radial speed, so the accretion speed, as a function of the sound speed. And you see that it depends on a few parameters. So m dot, the accretion rate, tau, which is the vertical optical depth, epsilon, which is h over r, and the radius. Let's now focus a bit deeper about some particular states. So we've been talking about luminous hard states a lot this morning, and I like that because those are the toughest ones to reproduce. So let's focus on them. So a luminosity above 10% Eddington, so we're at the top right of the hardness intensity diagram, and a slope of 1.6, 1.8, sometimes a bit smaller or higher, but that's the basic parameters, and a high energetic cutoff that you can see. Thanks to those parameters, we're going to be able to estimate m dot, tau, and talk about epsilon. So first of all, if you want to reach 10% Eddington in luminosity, you need m dot to be bigger than L head over c square. That's just the way accretion flows work. Any accretion flow has a radiative efficiency, and even the most efficient ones, you need m dot to be bigger than L head over c square. Second one is tau. There are some experts on that in this room, so I'm not going to talk about that much. But if you fit Compton models on the spectral shape, you can estimate tau, and you can see that it should be of the order of 1, so 0.5 to in this region. The third one is the biggest problem to me, because this one is the only one that is kind of model dependent. It kind of depends on your views on black holes, on accretion flow, sorry, on what you assume. Ingram assumed 0.2. Recent results that reproduce the spectra have found between 0.1 and 0.2. So I'm going to stay in that range, but this one you can argue. And then the last one is the radius. Andre gave a great talk this morning about the fact that this radius is not really consistent depending on the model. So you can have very different estimates. But whatever you do, your hot flow has to be in the luminous hard state, has to be between like the inner region, so between 2 and 30 RJs. So those are the ranges. I'm going to use those values. So m dot of 1, of L head over c square, sorry, tau of 1, epsilon of 0.2, and r of about 10. And we're going to see what it gives in the equation. So again, you could change those values. You could tweak them a bit by a factor 2, each of them if you want. But whatever you do. Yep.
3 minutes left.
Okay. Whatever you do, you're going to end up with a accretion speed that is close to supersonic, or at least sonic. So this is a big issue. I'm going to go straight to the point because I don't have much time. This is a big issue in most of the models, actually, unless you're magnetized. So thanks, Matthew, by the way, for mentioning that as well. So the results that it suggests is that the disks need to be magnetized, whether it's a SANE or SANE, I don't know how to pronounce it, a MAD or JED, you need a magnetized flow to do that. Now, if you go back to alpha, so if you assume a viscous flow, you can again link alpha to the accretion speed in the accretion flow by those two equations that again are like everywhere in accretion flow physics. And if you do that, you get an alpha of 5, exactly the one that Matthew showed, by the way. You get an alpha of about 5. So the problem now is that, well, you can't really do that with a viscous flow, can you? Because alpha is supposedly around 0.1, 0.5 sometimes in some simulations, but not much higher. So you have a big problem because your hot flow cannot really be viscous. Now, if you take that back to what we were talking about initially, the Lense-Thirring precession. It's not going to the next slide. Oh, yeah. If you take that back to our two initial conditions about the Lense-Thirring precession, you need the torque to be bigger and you need alpha to be smaller than epsilon. And if you actually write those two conditions in the hot flow, this is what you get. So you get that the Lense-Thirring torque is about 25 times too small to work in the hot flow. And you also get that alpha that you require is much, much higher than epsilon, also about a factor 25, by the way. So neither conditions are actually fulfilled. You're never in the right conditions in the luminous hard state to reproduce QPOs. The problem is, in those states, we observe QPOs. So how do you explain them? If it's not Lense-Thirring precession, it's something else. And if Lense-Thirring precession is not the process explaining QPOs in the luminous hard states, why would it be the process explaining the other ones? So we have a big problem here. Thankfully, we're kind of saved. So I'm going to finish on that. So my three conclusions. So the first one is that the inner flow needs to accrete at sonic speeds, even supersonic, depending on the estimates. And you can only do that with magnetized flow. The second one is kind of similar. It's that the associated alpha that you get from that is 5. And so you cannot really be viscous. So again, that's a similar conclusion, but expressed in a different way. And the problem you get from that is that the current solid body precession from Lense-Thirring does not fit the first conclusion here. You can't add those two conclusions, sorry, because in their assumptions, they assume that you were dominated by the viscous torque and the Lense-Thirring torques. So only two torques. And in fact, you need a third one. You're going to need a third one to explain observations. And this one has to be included in the calculation of the solid body precession model and see what happens. So it does not mean that Lense-Thirring precession does not work. It means that the current version where you have only two torques and you need to reproduce observation doesn't really fit those simple equations that I showed today. So thank you for listening, and I'll be glad to answer your questions.
Thank you so much. We have one question from Phil, and I'm not sure whether we have a question from Chris or whether he forgot to lower his hand. Phil, go ahead.
Thanks, and hi everyone. It's a shame I'm not there. So I was wondering if there's some freedom for the Lense-Thirring precession models in the assumption that you've made that tau is basically the observed tau, right? Because it could be that the tau that we see is just some sort of atmosphere, and the hot flow itself could be a bit denser than that, right? And we're just not seeing it because maybe it just doesn't get the seed photons. So is that an escape route for the Lense-Thirring solid body precession? So
that's a great question. I'm actually not sure. The problem is that's not how the current model is built. So maybe it could be, but you have to ask someone who's like an expert on that. So I wish Adam was here, or Chris, or like an actual expert on Lense-Thirring precession. But so I'm not sure, but that's not the current building of the model, at least. Okay, thanks.